indeed. So it will be a mix of very classical, very old-fashioned algebraic geometry and some modern stuff. So before going to explicit examples, I give maybe some general results, which might explain why do we care about involutions. So first of all, if say the field is algebraically closed, then there is a very classical theorem of Noethera-Kosterlyanova, which says that, so K is algebraically closed, which says that the Cremona group, rank 2, okay, it's actually generated by subgroup PGL3 and a single standard quadratic map. It's called the Birational Involution x, y, z goes to let's see, so y, z, x, z, x, y. And this has immediate corollary that the plane harmonic group is generated by involutions in this case. Simply because over the algebraic closed field, PGL3 simple, so the subgroup generated by involutions is normal, and you're done. Yeah, as I said, it's a very, very classical thing, proven in classical using classical tools. And it took I don't know, more than 100 years to generalize the theorem, actually to generalize corollary in field. It's a theorem. Let's say theorem. We do Lamy and Schneider. In Julia Schneider, so 2022, right? Which says that Cremona 2 over K for any perfect K is generated by involutions. Any perfect K. And well, manage the character is I'm going to work on removing this condition on perfectness of K. But in any case, this is much more, I mean, this result uses advanced methods of rational geometry, Sarkisian program. So it's actually, yeah, not that easy to show. And yeah, I think that's it for generalities. Another motivation could be that what are simplest finite subgroups? These, of course, subgroups of order 2. And there is a very, well, okay, there is a famous work of Dolgachev and Iskovskих about classification of finite subgroups in Cremona group of rank 2. But this work actually was preceded by the work of Bayle and Baville, who classified so all involutions in Cremona 2 over complex numbers. And I think I'll stay this classification in 5 minutes. But before that, let me maybe give you some examples. Examples of involutions would be my part. So of course, so I already gave you one. I gave you one standard quadratic map. Then of course there is linear involution, biregular one. But then we can yeah, let's I'll give you an example in how like classical people did it. So assume that I have a P2 I choose 7 points on it. 7 general points. I'll work over complex numbers now. Okay. Then I can consider the linear system of cubics passing through these points. Cubics through I. Okay. That has dimension 2. Dimension 2. Now take a general point or on P2. Okay. And I consider those cubics now which pass in cubics in my linear system, which pass through P. So P belongs to L. Okay. Good. So I have this pencil. As we know, a pencil has 9 base points. Okay. So I already gave you 8 of them. I can now find the 9th base point. And I define a self-map of P2, rational self-map called gamma, which sends P to 9th base point. 9th base point of the pencil. Okay. And well, when you check that this is a Birational map of P2, it's actually not very easy to write down explicit equations. I think they have a high degree in this case, but classically it's known as a Geyser involution. Geyser involution. We can now do a similar trick by taking, it will be my second example, by taking this time 8 general points. On P2. I call C again the pencil of cubics for them. Okay, and now I take let me call maybe, well, P9 will be the ninth base point. Will be the 9th base point. Okay. Now I take a point on P2. I find the unique cubic in my pencil which passes through it. Call it maybe CP. Yeah, CP. In my pencil contains P. And I define a map called beta. I define the map beta. P goes to beta of P, which by definition will be minus P with respect to the group law on CP. Where I took P9 as the 0, as the origin. Where P9 is 0. And once again, you can check that this is an involution, and it's called Bertin involution. Once again, I think if you want to real equations, the degree will be like 17 maybe. And I think it's time to state the theorem, which is the theorem of Bayle and Baville. The theorem says that if you want to over complex numbers, every involution is conjugate to one of the following. It's either linear, is conjugate to linear, or Gaussian involution, or the linear involution, or the Jankier involution. Which is easier to give in local coordinates. So in local coordinates, is something like xy goes to x p of x, or y, where the degree of p is a polynomial with no multiple roots, 4 degree. And that's it. It's a very elegant classification. We have only 4 cases. What time is it? 7:32. 32. Good. And basically, our work with Vanya, Frederica, and Susanna was about generalization, not generalization, but about transferring the theorem to non-algebraic closed case, for example, to real numbers. What against? I mean, spoiler: this theorem fails dramatically in over real numbers. So the explication is much more involved. But or maybe giving you an idea, let me once again remind you the general strategy, like how would you actually attack these kind of problems. It was already partially mentioned by Andrea on Tuesday or Monday. So, how would you classify actually involutions in Cremona group? There is a classical strategy. Have a rational action on P2, or actually on any variety, but let's stay on P2, rational action. You can regularize it.
What is G?
Any finite group. But you think about involutions. It's finite group, yeah. What regularization means? It means that there exists a smooth projective surface that's rational over A. And then an embedding I over G in the automorphism group of this surface. Let's fix maybe a rational map from S to P2. Such that my group G can be obtained as follows. So G is simply psi of G, psi inverse. Essentially, I replace the birational action on P2 by biregular action on some surface. Now I can apply covariant version of MMP. And what I get in the end is the Mori fiber space of dimension 2, which is either the Petzer surface or a conic bundle with some minimality assumptions, of course. So it's a G Petzer surface, meaning that equivalent Picard 1 or the conic bundle, meaning that equivalent Picard is 2. Okay. And now reclaim very difficult is that actually the conjugacy classes of subgroups in BIRP2 are in one-to-one correspondence with G birational isomorphism classes of such surfaces, of such pairs. Of such pairs. Let me go and start. So the moral is that if I want to describe conjugacy classes in Cremona 2, I need to classify such Mori fiber space in dimension 2 up to G birational equivalent. Okay. And essentially this was what was done by Bail-Baville and later by De Ferney, Logachov, and Eskovskih, and many other people for different G. But of course, today we're interested only in the case where G is a group of order 2. So now we could ask what are regularization of these classical involutions, which are written here. Well, the name already suggests that this should be somehow related to the Petzer surfaces of degree 2, 1, because we know that on the Petzer surface of degree 2 have classical desk convolution of the double curve is known as Gaussian involution. So this one is regularized on the Petzer 1, the Petzer 2, sorry. The Bertini will be regularized into Petzer 1, of course. And the Jonquière will be regularized on conic bundles. So this one will be regularized in conic bundles. Okay, so this is the strategy. Now you could ask a very natural question. Actually, why these involutions are different in Cremona group? Okay, why they are not conjugate to each other? And this was an interesting insight that you can distinguish them by looking at the fixed curve. Namely, same. Two involutions are conjugate if non-leave in Cremona group. Non-leave their fixed curve, their fixed curves are isomorphic. This immediately gives you that these involutions are actually to each other. Why? Because imply that non-conjugacy of Bailey-Baville involutions. Why? Well, I told you that Geyser involution is regularized by the 2. And the fixed curve in this is the propagation curve the quadratic curve you want. In the case of the Batso one, it's again ramification curve. It's a static curve whose anti-canonical model lies on a quadratic. And in this case, the fixed curve is simply the curve which is given by equation y squared equals p of x. So it's a hyperelliptic curve.
Does this claim work for any field or just complex number?
Complex numbers. That's somehow the point of this talk. Yeah. Maybe okay. Yeah. Yeah. Maybe I will say something about stable conjugacy later, but yeah. So maybe indeed it's time to formulate the results somehow. So what's the point? So actually, I will not give you the full classification because it's actually very long. So just two features. So well, results of our work with Vanya, Frederica, and Susanna. Well, first of all, instead of 4 classes of involutions, we have like 13. But then maybe the result, which is very easy to appreciate. So let me emphasize that here everything's overseen. Very important. But an important corollary of our work, actually, work started with this question, is that the fixed curve does not distinguish the conjugacy classes anymore, and somehow really fails dramatically. So, namely, if I can put it this way, so if C is a real curve, it's real curve. And then we have some technical assumptions. I think the genus is at least 2. And we have at least 2 connected components. That's correct. Yeah. Then real harmonic group over real numbers of rank 2 contains uncountably many evolutions which fix C. Put hyperelliptic. Hyperelliptic. Yeah. Real hyperelliptic character. Yeah. Actually, we can prove the same for rational curves. So there is no such nice correspondence anymore. You cannot distinguish the conjugacy classes just by looking at I mean non-conjugate, non-conjugate inversions. Non-conjugate. Non-conjugate inversions. And so yeah, so this is basically the work is split into 2 parts. First, we classify all involutions. We put them in one of these 13 classes, and then we put the corollary. We present these families of non-conjugate involutions.
Sorry, can I ask a question?
Yeah.
Sorry, the 13 classes in part 1 are 13 different conjugacy classes of involutions.
So 13 classes, they're pairwise non-conjugate.
Okay, so I think I'm confused because any one of the involutions of part 2 is conjugate to one of the 13 classes.
Every involution here,
Yes.
it belongs to one class here.
Oh, sorry, okay, sorry,
I
okay,
mean,
okay.
okay, it's
Sorry,
actually
sorry.
against particular involution. It's an involution. I mean, involutions which are about here. These are involutions which come from conic bundles. They're regularized on conic bundles. Okay. Here you have conic bundles. You have the beta surfaces, and basically an interesting unexpected type of involutions that we discovered here. Maybe I give this example. So basically, I think we didn't expect much from the beta surfaces, namely any new examples, maybe, or a lot of new examples from the beta surfaces. But we discovered actually a very interesting involution, exotic involution of the beta of degree 2. We call it Kovalevsky involutions. New involution. On real beta 2. Actually, if you are over complex numbers and you have an involution which acts minimally, so with this condition on the beta 2, then this automatically implies that this is the Geyser involution. Okay, there are no other involutions, so it must be the involution of the double cover. It's not the case anymore of reals. Namely, okay, how to put it very shortly. Why it's called Kovalevsky involution? Because it's actually beautiful result of Sophie Kovalevskaya, who was working on problem of abelian reduction, abelian integrals to elliptic. She proved that the claim is the following. So we take a quartic curve on P2, real one, real smooth quartic. And we know that there are 28 bitangents to this quartic, right? But they have sometimes tricky configuration. It like happens sometimes that there are 4 bitangents which intersect in one point. Okay. Then 4 bitangents to be meet in one point. If and only if there exists a involution kappa, regular of two, which preserves D, quartic B, and has an isolated fixed point. I take a double cover of P2 ramified at such a special quartic, and I lift my involution to this double cover. So the lift of this kappa to the beta 2 associated will be my Kovalevsky involutions. I would like to emphasize that here, the geometry of this B and of the corresponding surface is really special. So since we're working over real numbers, the beta surface can have different type of real loci. Okay, quartic curves, as we know, they have most 4 ovals on P2. There are some configurations, possible configurations of these ovals, and in this case, we can write down equations for B, for S, for everything. In this case, we'll have some B. Namely, the real locus will look like it will be either either circle or nested circles. A priori, you could have different things. You could have 4 nested circles, 3 circles, but here it's very special to be why the 1 circle or 3 nested circles. And the real locus of this of the surface S will be either sphere in this case or a torus here. So that was unexpected. I should finish, right? Yeah. And that was unexpected. And my final remark is that, well, it's about the second point here, how we construct non-conjugate involutions. Construct non-conjugate real involutions with the same fixed curve. We look at conic bundles. Napoleon form. So, well, just write something like that. A, B, C, H are polynomials, of course. So T is my coordinate on the base, right? And the involution will be just fiber-wise involution. It does not mean the base. And then if you take the discriminant of this conic bundle, you can keep discriminant. This discriminant actually defines discriminant defines your fixed curve. Yeah, let's say W equals this. In general, it's a hyperelliptic curve. The degree of discriminant of delta is at least 6. And now I can keep this discriminant and vary h. Okay. By varying h, I get many conic bundles which are not birationally isomorphic to each other, but the fixed curve is still the same. Okay. So actually, well, if you like work in birational geometry dimension 2, normally, and if you want to study like self maps of conic bundles, we have this machinery of Sarkisov programs. So you have a lot of singular fibers here. Then the classical results tells you that all transformations are fiber-wise. Okay, many fibers here. So essentially, we should be able to decompose these self-birational maps in fiber-wise transformations of conic bundles. Okay, but we're not able to do it geometrically. So we find such a decomposition. And instead, we used essentially the Witt theory of quadratic forms here over the function field. To understand when such two conic bundles are birational to each other by looking at corresponding quadratic forms. Okay.